Good day to all of you. So, we continue from where we left off in the last class. Today, we shall try to integrate the control system, the PWM and the DC-DC converter all together and see how the whole closed loop system is put in place. And then we shall try to have a look at how we go about choosing the controller parameters for any given system. Okay. So, the objective of today's class is to actually have a controller which is designed to meet some performance specifications. Now, this we shall do by two methods. One is by what should we say, tuning controller directly on the system. So, directly on system which could be a hardware platform or it could be a simulation platform. The other method is from the model. We have developed the small signal model of the DC-DC converter. Using that model, we use the root locus technique. And then from the root locus technique, we arrive at controller parameters. These controller parameters are arrived at by iteratively looking at the root locus of the plant, closed loop system and the step response, and then after many iterations you can boil down to the appropriate value of the controller parameters. These will be populated or included in the hardware or simulation platform. So, this is how we will try to address the issue of controller design. The tuning the controller directly by trial and error is quite a popular method which is used by many people, because it does not involve doing a lot of maths and modeling, and it also handles many uncertainties and unmodeled dynamics, lack of our knowledge of the system. All those issues are directly handled. However, this has to be done directly on the final target system or one level above, that is on the simulation platform. Whereas, in this method, mathematical modeling of the system, obtaining the transfer function, from the transfer function the root locus, identifying what is supposed to be the best closed loop pole position, then from there identify the control parameters and then plug it into the hardware or the simulation platform and see the response. So, these are the two methods. This is a much more formal method, can be applied for many complex systems, but we will look at both these methods. So, first tuning directly. One of the more popular methods, the Zeigler-Nichols method, where the parameters, that is the Ki parameters, the PID parameters, the proportional, integral and the derivative parameters are sequentially tuned till the response is satisfactory, and then finalizing on the values appropriately depending upon what is the performance specifications. Of course, we are not going to try exactly the Zeigler-Nichols method. We are going to try something similar, use something similar like the Zeigler-Nichols method, tuning first the integrator parameter, the proportional and then the derivative. Derivative is actually, if you see in our earlier class, is a gain that we are trying to introduce in the high frequency zone. This is the omega axis and this scale is logarithmically distributed, and this is the gain in dB. Remember from the old classes, we have divided the zones into the low frequency part and the high frequency part. The integrator is something like this, it keeps going down at minus 20 dB per decade. This is the slope of the integrator. Refer back to the earlier classes. Now, the proportional part, the moment you introduce the proportional part, we see that it adds a 0 and therefore a plus 20 dB per decade. So, the plus 20 dB per decade and the minus 20 dB per decade of the integrator gets compensated, and there is a flattening of the controller curve, gain curve, and somewhere at a much higher frequency we are trying to introduce another 0, the derivative part, which tends to increase the gain, contributes a plus 20 dB per decade, and much later it flattens out because of the presence of a pole, because no derivative is ideal in the ideal sense does not exist. There has to be a pole at a much later state. Now, this introduction of gain increase here in the high frequency zone, this is gain increase in HF zone. This is a dangerous zone in some sense, because this is where noise is predominant in the high frequency zone, and introducing the gain here is a bit dicey, and you will have to be very careful. System to system you may have to tune this gain. Preferably do not use the D portion. If your performance specifications are met, with the integrator and the proportional, stop there. Go for the D only if it is absolutely necessary, and if you are not able to improve the performance with proportional and integral controller. So, for most of the cases, just the P and I portions are sufficient. The D portion you can use it only if necessary, and that can come in at a later stage of the design. So, we shall try to first tune the I portion, choosing which parallel that you would like to use, and then use the proportional cutoff point for improving the dynamics, because we are trying to improve the gains here. So, this is the approach that we are going to follow. Choose K I parameter first, and then K P parameter next, and only if required go for the K D parameter. So, if we look at our system, let us say that we have a buck converter which is something like this. So, we have a switch. I am representing the semiconductor switch by a transistor and a diode, but remember that this transistor could be a MOSFET or an IGBT depending upon power levels. So, we have a buck converter here. Now, this buck converter is appropriately driven by a gate drive, which drives this transistor with respect to its emitter or source. The signal for this gate drive will be coming from a pulse width modulator. So, here you will have your PWM IC, which is going to give out signals in this fashion, where the on time can be varied. This is the switching time, switching period. The on time can be varied. So, which basically means that we are giving a duty cycle input to the buck converter. Now, to the PWM are two inputs. One is a carrier, triangle or sawtooth carrier, which basically keeps the reference for the period, and other input is the control voltage, which basically modulates this carrier to give the duty cycle, as we discussed in the earlier class. Now, the output of the controller, the central portion on this, This is the controller, the output of which would be the control signal or the control voltage to the PWM or the pulse width modulator. Now, let us say this controller is a PI controller to start with, and the input of the controller is actually coming out of a compare block, which compares a reference with the feedback signal. So, we will call this the compare block. Now, let us say that we would like to control the output voltage. If you are controlling the output voltage, then you provide a output voltage reference and you feed back a signal which is proportional to the output voltage. If you are controlling the inductor current, then you will be setting the inductor current reference, feed back the inductor current, or if you are controlling anything else, that particular parameter is reference has to be set here. So, let us say we set the reference for the output voltage, which means that you will need to feed back the output voltage sense that and bring it into the controller, and this is how you feed back the output voltage V naught feedback. Note that here for now we are directly feeding back the output voltage to the compare block. In practice, you do not do that direct feedback, it passes through another sensing circuitry. So, actually you would see a block here, and that block is called the sense and isolation circuit. So, for now we will assume that the sense and isolation circuit is there and it has input to output gain of 1 unity. We will later on look at what this sense and isolation circuitry is. That is, you need to isolate this ground with the control ground to protect power and the signal ground from the power ground, and you need to sense and provide a voltage here which is proportional to the instantaneous value of the output voltage, the control voltage. So, that is the job of this sense and isolate circuit, this portion, which will involve probably opto isolators to bring in the isolation. Now, our main aim is to focus on this block. How are we going to tune this? Now, this block in itself is having 2 parameters. One is the Ki, the integrator scaling factor, and the other is Kp, the proportional scaling factor. And we know the equation of the Pi, which is, if this is the error and this is Vc, this is Vc, and we know that Vc is equal to Kp into E plus Ki into integral of E dt. So, this is what we want to achieve. So, what do we do step by step is first we set up the open loop system. Which is like this. The open loop system would mean everything from here, the comparator block, controller, PWM, and this DC-DC converter, and the feedback, sense isolation up to this point. We break that up to that point. Now, set up this open loop system, and then next put limiters across integrator and we see this is very important, very essential. What it basically means is we need to limit the voltage swing at this point. Remember that this is a pulse width modulation system where the triangle has a limited voltage, limited lower point and a limited upper point, and your Vc swing must fall within that limit. So, therefore, it is very essential that you limit the output of the PI controller within the limits to stay within the limits of the triangular carrier. And then the third point, in the open loop, keeping system in open loop, check phase relationship. This is very important. When V naught ref is increased, V naught feedback should increase, then you are having proper phase relationship. When V naught ref decreases, then V naught feedback should also decrease, only then you have proper phase relationship. So, what it basically means is that you have a potentiometer here, increase V naught ref, let us say it is set at 5 volts, increase from 5 to 6 volts, this would increase E, will increase the output of the PI, this will increase Vc, which will increase the duty cycle, should increase the voltage, and then should increase V naught feedback. When you are doing the open loop test as like this, it would be a good idea to make, when you are doing this, make K I equal to 0, K P equal to finite value, because if you have K I as a non-zero value, the implementation of the I portion is a capacitor. The capacitor will invariably charge up, and it will charge up to the maximum because it is in open loop. Therefore, bypass K I or make K I is equal to 0, bypass the integrator or make K I is equal to 0. So, that when you increase this will increase, V c will increase or decrease, D will change, and this will result in a change in V naught. So, an increase here, increase in V naught ref should be felt as an increase in V naught feedback, decrease in V naught reference should be felt as a decrease in V naught feedback. Then your overall loop phase relationship is okay. If it is not okay, if an increase here is resulting in a decrease here, you will have to change the phase relationship in any of these component blocks. In the PWM, the output of the PWM can give you plus or minus 180 degrees phase change by choosing the output across the collector or the emitter point of the PWM IC. That is one possible point. There would be op amp in between, op amps in the PI, where you could possibly have 180 degree phase shift achieved, and also in the op amp at this compare point. So, if this is 180 degrees out of phase, change here results in a 180 degrees out of phase change here, adjust the phase relationship in any one of the blocks here, so that you make these two phase change relationship same. An increase in V naught ref should result in increase in V naught feedback, a decrease in V naught ref should result in decrease in V naught feedback. Only then can you go forward. Next, so after that, enable again, bring back, enable the integrator, close the loop, make K p equal to 0, K I equal to very low value. Start from a very low value like 0.01 or so. So, what does it mean? Here you are making this connection, close this, enable the I portion, because you want to use K I now, make K p equal to 0, the K p portion right now focus only on I, proportional will come back later, and start with a very low value of K I, or in other words, this is generally implemented as 1 by RC integral of EDT, the implementation in op amp, things like that. It would mean a very large value of C. So, in other words, very low value of Ki means, this implies start with a very large value of capacitance C of the PI controller C. Now, when you switch on the system and observe the switch on transition, the switch on transition dynamics T versus, let us say, V naught or V naught feedback. After you switch on, V naught feedback is supposed to come to the V naught ref value, So, by adjusting the C value, Ki value, very low Ki value will imply that it will take a very long time for the system to reach a steady state, and sometimes if there are overshoots, it can take a long time before they start coming down, because you are using only Ki. So, you will see this, if this is Ki, Ki is increasing like this. So, basically, if you look at the omega curve, we had the I minus 20 dB per decade. You are trying to choose different parallels by choosing different I's and therefore, different bandwidths. Unity gain bandwidth. So, this bandwidth will increase as Ki increases, So, that is what you will be seeing. It will try to become faster and faster, but of course, the overshoots may also increase. So, you stop at some performance where it reaches steady state at some particular time as set by your performance criteria, and then freeze on the value of Ki. Okay. Stop the value of Ki, which basically means that you would have chosen one particular value of Ki parallel, the integrator parallel with a particular bandwidth. So, you fix that. So, your low frequency and the steady state portion is fixed, and you know that in the steady state the error is going to be 0, because the DC gain will be infinite. Now, we need to fix the proportional portion, which will take care of the high frequency dynamics. So, the proportional portion is fixed next. K I is fixed based on response as viewed on the scope or simulation platform. Then next, start increasing Kp value from 0. So, as you start increasing Kp value from 0 and then look at the transient response, with a particular value of that integrator, you would see that, let us say, it had a profile like that. You should probably now be able to improve its dynamics something like that. That is, you are improving the high frequency dynamics. Steady state is still governed by the integrator portion, and this is due to the P. So, this is what you would see happening when you try to keep increasing P, keep on increasing Kp till you reach a satisfactory by visual, in a visual manner, a satisfactory response, and freeze Ki and Kp value, and these values of the Ki and Kp are the ones which you will be using in the controller. Most of the time when you are working with the hardware, every time you will have to switch this on and off and try to capture on a storage scope to study that. A better way would be to V0 ref, which is a fixed DC. Superpose a pulse waveform like this, then you would get V0 ref, which is of this nature. Set this period to a very low time period, let us say 1 second, and there is sufficient time for you to see the response of the system. So, initially you would see that the V0 or V0 feedback goes like that, then like this, so on. And if you trigger your scope for this edge, if you trigger the scope for this edge, then you will look you will have a standstill waveform on the scope, and you could use the potentiometer to tune the K I K P values to see the improvements in the response, transient response. So, this way you could tune it, and then after the tuning is over, the pulse portion which you use for superposing can be removed, and then you can give the proper V naught ref, something like this DC later on. Okay. So, this is the process of tuning the controller directly onto the system. Let us view this on a simulation platform and see how we go about tuning it. This exact circuit can be simulated on many platforms. Here, let me demonstrate to you on a few open source softwares. There is the GEDA, the GNU EDA tools, electronic development and automation tool. There is NG Spice, which is an open source, this one open source software, and of course Octave. So, these three have been combined, have been taken together, and some tools have been developed which can be used for simulating the circuits. So, GEDA is primarily right now being used for schematics in this particular exercise. NG Spice is actually used for performing the simulation run, and Octave GNU plot is used for actually plotting and displaying the results. Of the results. So, let me demonstrate to you this. So, first let me enter the schematic in GDA. The schematic will be something like this. So, let us take the buck converter itself for working this example. So, now let me switch over to a platform computer. I have used GDA, I have opened GDA. This is the schematic editor of GDA. Okay. And let us draw the circuit. I will use the circuit components and draw the I will probably use capacitance. I will need to use a diode. I will need to have a source, a DC source, will convert that to a source. I will need an inductor, then I will need a power switch, and of course, I will need a resistor. Okay. So, let me rearrange all these. So, this is DC of let us say 12 volts. This is V in, and let us have a switch, diode for freewheeling, inductor, capacitance, and the load resistance. So, we position them and let me zoom. Like this, use the wire, join the components, like this, just like any schematic editor. So, we have our basic circuit done. We can then enter some typical values, we will do that later, and then we need to put in the controller. So, let us take from the block first PWM, we need that, we need PID with anti wind up, we need that, we need compa block, we need that. So, let us quickly put them together like this, and we use the wire, connect them, so we have connected. So, we will be capable of editing the PID block parameters here later, we will do that. So, we have this setup. Now, we need to add one more important thing, an include file. Now, this include file, I will place it here. This basically points, this file basically points to the you see that we have added these components. These are generic switches, generic diodes, and here you have the PWM block which has logic inside, the PID block with the logic inside. Now, all those logic and the equations are in a file called a sub circuit file and sub file, and you have to point to that, so that the model can be taken from that file. So, just include that file there. So, after you have included all that file, so we will have this completed circuit. Do not forget to put the ground. Every circuit should have a ground. In SPICE, you must be knowing that all the calculations are done with respect to a 0 node, the ground node. Now, I have given V in as 12 volts, and this is the switch which is named XSW. Now, remember here I have used a label, a generic power label, and named this junction as NVD point, and there is another node here, this is NVC, voltage across the capacitance. L is set at 10 millihenries, R at load is set at 1 ohms. See, if this is 12 volts, this is a buck converter, let us say we set it at 5 volts, it will be 5 by 1, 5 amps, 5 into 5. So, 25 watts of power will be sent to the load. So, if you look closer, right now I am keeping it at open loop. This is a reference value of 0.5 control voltage which I am setting for the PWM stage, which is set at 10 kilohertz. The output of the PWM is shown as NVG, just this one. I just removed the PI for now, and look at the include file where right now I am using edt01.sub, which contains all the equations for the underlying component blocks. Now, this can be simulated. So, in open loop can simulate and see the various waveforms. So, that is why these have been labeled. Okay. So, let us have a look at the various simulate it and see how the various waveforms come. Okay. Let me go to the command line and run, I will write ngsim, the schematic file is executed. So, on executing, first the netlist is generated. So, this is the netlist of the schematic that we just saw, okay. RL, L, V, and D, C, and the PWM, okay, pointing to that include file, all those things. And then we need to set some parameters. So, let us choose the analysis type. Let us say we choose the transient analysis, and we will give the print step, let us say 10 microseconds, and the final stop time of 50 milliseconds, let us say, and we request ngSpice to perform the simulation. See that the simulation is running, and then we will be able to see the waveforms. Now, here the waveforms, you have time and we have a host of node voltages and branch currents. Okay. X axis, of course, we want it to be time, and the y axis we would like to see the waveforms across the output maybe, and maybe the waveform which is given as pulse width to the switch, and probably even the current here. So, let us see these waveforms. So, one is NVC, V, NVC, and also probably NVG, the gate waveform. So, this is the waveform that you are seeing, and you see that it is naturally going at settling at 7 or 7.5, because we had set some arbitrary value of. So, let us say you can zoom in. This is the pulse width, something like 70% or so, mod waveform which is seen at the gate of the power switch. And if you would like to see the waveform of the inductor current IL, we would like to see the waveform of the inductor current IL. Though it shows a smooth, when you zoom in and open it out, you will see the triangular wave shape of the inductor current of the buck, just like as we see in a regular buck converter, up and down in the triangle fashion. Okay, this is the open loop system, and we would like to tune the controller. So, let me show you the closed loop system, which I have already built. So, the circuit is like this. So, you see the closed loop system here. This is the buck converter. I am giving a reference, a pulse reference, like I just discussed. This is the reference V naught. Let me zoom into this point, plus minus I am feeding back the voltage across the capacitor at this point, the labeled point. Output of the controller goes to the PID. I have set D 0, I am not using it right now. It is limited to plus minus 1, lower saturation and upper saturation of the PID. PWM signal is a triangle carrier having minus 1 to plus 1, which has a frequency of 10 kilohertz, Ki 10 and Kp 1 value set, and the output of that goes to the power switch. Okay. Note this point here. This reference is set for now as a pulse which is having 5 volts, and from 5 volts it goes to 6 volts and then back again to 5 volts. So, it is a pulse of 1 volt superimposed on 5 volts, and it has 5 milliseconds to 10 milliseconds, 5 milliseconds on time, 10 milliseconds period. Okay. So, that we will be able to see the dynamics of this. So, this let us simulate and see how the wave shape looks like. So, we go again back here, ngsim buck circuit.sch schematic. So, you see the net list gets generated, all these, the summer, the PID, the switch, RL, L, V in voltage, diode, capacitance, the PWM block, the include file, all those things captured from the schematic and the net list gets generated. And I could use the old values of transient analysis values, ask ngSpice to simulate. ngSpice will simulate and put the data into a raw file, and then we are ready to view the outputs. So, time, we would like to view time and the voltage across the output capacitance. We would also like to view the voltage of the control voltage, the pulse V naught ref. So, you see that for those values of Ki and Kp, this is V naught ref, 5 to 6 volts every 5 milliseconds up and down. And this red waveform is the output voltage which is tracking the reference waveform, and then the dynamics occurring, and then tracks reach steady state accuracy. then starts coming down. So, this is what it is trying to do. So, you can try to tune your Kp and Ki to improve the responses. So, in this way you iteratively manipulate. Let us say we go here, increase Kp value, Ki value is set, let us say increase Kp value, let us go make it 10 and save the file, go back again here, regenerate the netlist and ask ngSpice to simulate it. It will give you the waveform and let us view the same waveforms. You see, because we have increased Kp, the dynamic response has improved and it is able to go within within that pulse period itself up to its stable point, comes back to the stable point, so on. So, you can play around with the Ki and Kp value and get better and better dynamic responses, and once you get satisfactory response you stop, because there are infinite solutions and you need not try more than to get a better way, that is, when there are infinite solutions you do not try to search for an optimum in this trial and error method. Trial and error method is just to give one solution, so that it just works. Getting an optimum solution is another ball game, where you have to mathematically try to extract the optimal out of a cost function. So, with this we stop here at this point and continue in the next class with the other method, which is the root locus method. We use the model, the small signal model of the system, and then try to obtain the root locus and then the controller parameters. This is one method what we discussed today by the trial and error approach, or the Zeigler Nichols method, where you try to first tune Ki, then Kp, and then view the responses. In the next class we shall discuss the root locus method. Thank you.